5.3, this is the definite integral. So just as a quick review, we're going to look at summation notation. This bottom number here is your starting value, your starting index. And this is a Greek letter sigma. That's why it's called sigma notation, but summation because we're adding things. So you're going to plug in the starting index 0. So if you plug in 0, you get 0 cubed. Then you increase this by 1. So now we're going to have k equals 1. Since summation, you're summing, we add. We plug in 1. And you keep on going. So now you're next, you're going to increase by 1. So now you plug in 2. Then you plug in 3. Now, this number here is the last number you plug in when you stop. It's not the number of terms, but the actual number you plug in. (27, 28, 36). Hopefully that's right. You can try this next one on your own. So let me plug in the first number, which this time it's 1. And you keep increasing by 1. And you stop when you get to 3. 0, 4 minus 1, 9 minus 1, and we get 11. So it's a quick review of summation notation or sigma notation. All right, what are we doing here? So this is a right-hand Riemann sum. Note we have n rectangles, and we start at A and we end at B. So if we want to know the width of each rectangle, how wide is that? We call that our delta x. We got to figure out how far it is from here to here, which is going to be B minus A, and divide by the number of rectangles n. That tells you how wide each rectangle is. So now, to get the height of each rectangle, if you look, the first height is going to be right here. So the height's going to be at x1, so we need to know what x1 is. And then the second height's going to be at x2, so we need to know what x2 is, so that's what we have to find. But looking at this, we're starting at A, so it's A, and we're moving over delta x. So x1 is going to be A plus delta x. And delta x is B minus A over n. Now how about x2? Well, here's x2. You start with A and you move over delta x twice. So it's A plus 2 delta x's. And I think you see a pattern forming. How do you get to x3? You start at A and you move over delta x 3 times. How about x4? You start at A and you move over delta x 1, 2, 3, 4 times. Clearly the pattern's been formed. So here's a question. I'm going to add another one here, x of n. How do you get to the kth term? We'll follow the pattern. We start A, and we move over delta x k times, so it's k delta x. That's the general term for any kth rectangle. And then the last one's going to be the nth one. So you start A, and you move over delta x n times. And delta x is b minus a over n. And here's what's cool. The n's cancel, and the a's cancel. And you're left with b, what should be the right answer, because at b, we're going to get our last rectangle. And that is correct, because at b, that's the height of our last rectangle. So that's our x of n. Now, what are we going to do with this? Well, let's look at the area. The area is approximately. It's going to be about. It's not exact because we have our error. Remember, all this is extra. All those little pieces are too much. And then here, we're missing pieces, so we're approximating. Now, the area of a rectangle is base times height, right? So I'm going to do the height of the first one times the base plus the height of the second one times the base. Height of the third one times the base. And then we're going to do the kth rectangle. So plus dot 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 plus the height of the kth rectangle times the base plus dot dot dot. And the last one is going to be this rectangle. The height of the nth rectangle times the base. Let's keep going. How do you find the height of this rectangle? The height is the value of the function. Here's our function f of x. Here, it's f of x at x1. So h1 is f of x1, and the base, all these widths are delta x. So we're going to have a delta x plus f of x2 delta x, f of x3 delta x, f of xk delta x, and f of xn delta x. Running out of room here. I'll start further left. Well, I can write this two ways. So we're going to put all these in for x1, x2, x3. So now we're going to get f at a plus delta x, f at a plus 2 delta x, plus f at x plus 3 delta x. So just a reminder what's happening. I'm replacing these x's here with the values we found. And so on and so forth. Now I'm really going to be scrunched for room here. So let me zoom in and write smaller. This is going to be x plus k delta x's times the width delta x. And then this is going to be x plus n delta x's times delta x. Wow. Really running out of room. Now, in summation notation, the area is going to be about Now, what's the general term look like? We found our general term. It's our kth term. So that's going to be f of x plus k delta x. You know what? I'm going to write this a couple different ways. Let me start simpler here. It's going to be the height at the kth times the width, delta x. So just a reminder how these sigma notation works. You plug in 1 first, and that's going to be f of x1, which we have here. Then you plug in 2, f of x2. Then you plug in 3, that's f of x3. Then you plug in 4, and you stop when you get to n, so f of xn is our last one. So that is our sigma notation, but also we can replace f of x but what is x sub k? Well, here's our x sub k that we found. So it could also look like this. And delta x is our width of each rectangle. So this is the height of the rectangle, that's the width. Height of the rectangle, that's the width. Or the final form, we can write like this. In place of delta x, we can put b minus a over n. So it could look like this. F of x plus k, b minus a over n, times b minus a over n. All three of these are equivalent. I think this is easiest to understand. This gives us the most information. So all of these should make sense. So I've written my formula. But I call it, okay, but that's different. What's that limit there for? What is this? It doesn't make sense, but let's make it make sense. This is like the key moment of the lesson, the aha, like, wow, this is cool. So this is a midpoint Riemann. Let's change it to a right-hand Riemann. And if we look at the area, we see a lot of error. What are the error pieces? Just a reminder. Let me shrink this down. The error is I have all this extra junk here. Extra junk. Extra. All this is extra, and I'm missing all these. Now let's start with less rectangles. Yeah, let's start with less. If the least, like we start with 4 rectangles, man, error huge. Look at that. That's a big error. Big error. Big error. All these big, missing piece, big. Watch what happens as we make the number of rectangles increase. What do you notice? Do you see how these errors start to get smaller? And watch, that's 17 rectangles. That's 25, 26. Let's go up to 50-ish. That's almost 50. Look, man, little tiny little error pieces all along the top, getting smaller. And let's just keep increasing the number of rectangles. And as you see that, what you should notice, man, those little extra pieces are getting smaller and smaller and smaller. And when I get to 100, man, they're little tiny little nibs here. And the idea, as the number of rectangles goes to infinity, all these little error pieces are going to approach 0. And it's no longer going to be an estimate, it's going to be the exact value. As the number of rectangles increases, we get the exact area under the curve. Pretty cool. That's what this formula is saying. I'll explain what net area is, but the actual area, if we let the number of rectangles go to infinity, because remember n, this is the number of rectangles. N is the number of rectangles. in our formula, every n you see. So as n goes to infinity, this goes to infinity. That means the number of rectangles is going to infinity. So this formula is what we use to get the actual area. That's what this whole chapter is going to focus on. But what is net area? We couldn't call it area, and I'll explain why. If we just said area, and we did some Riemann sums here, and I do a right-hand side, let me draw these for you and explain real quickly what's going to happen if we did this. I know it's not a pretty picture, but I think you're getting the idea. Okay, if we did those Riemann sums, and we're getting the area, and we would call this x1. I'm just going to write down, it'll be f of x1 times delta x, right? Well, and you're going to keep adding these, but here's my thing. What's the value of f of x1 there? It's going to be negative. This first one is going to be a negative value. Your delta x is always positive because that's your width. But now think about this. All of these are going to have negative heights. And then your area is going to come out negative. But that makes no sense. Areas are always positive. But you're going to get the answer, you can get the area of that, but it's going to be a negative area. Well, so the term net area has come up where any area below is negative and any area above is positive. So your net area, you take the area above and you subtract the area below to get a net area. So that's the definition. Now, as we read this, consider the region R bounded by the graph. So here's a graph of f. Here's the x-axis. And the regions bounded between are here, here, and here. That's the area enclosed by the x-axis and your function. The net area R is the sum of the areas of the parts that lie above. So you're going to add these areas above minus the areas below. So it's the areas above minus the areas below is the net area. So go ahead and try to do A through E. You're going to go ahead and pause the video, and I'll come back and give the answer. Welcome back. So the net area from 0 to 10, I take the area above, which is 100. There's no area below, so the answer to that is going to be 100. The next one, 0 to 20. Here's 0, there's 20. So I take the area above, which is 100, minus the 50 below. It's going to be 100 minus 50, or the net area will be 50. The next one, we're going from 10 to 20. It's just the area below. There's nothing above, so that's going to be negative 50. 0 to 30. Well, it's going to be 100 plus 30. 130 minus 50. And that should be 80. So it's going to be 100 minus 50 plus 30, which should be 80. And the last one, 10 to 30. We're starting here, ending here. So that's going to be negative 50 plus 30 for a net area of negative 20. So that's what net area means. So areas are always positive. So the term net area was invented, I would guess, or I would say. And that's what that means. Okay. Here is the pinnacle. This is like, I don't think you realize how amazing this statement is going to be. I don't think you recognize it or even understand the power of what's about to happen and the beauty. Because in the first section, you found antiderivatives. And you learned, oh, this means find the antiderivative of f of x. And the variable is x. And you're like, okay, I can do that. And you found all these antiderivatives or backwards derivatives. We called them indefinite integrals because there were no numbers at the top and bottom. It was indefinite. When you have a starting number and an ending number, it's called a definite integral because you have a definite start and a definite end. And this will all make sense as we go on, what those a's and b's represent. But this thing that you did with the a and b, now it's going to be the limit we just looked at. And remember what this represents, uber important. This is the height of the rectangle. This is the width of the rectangle. And this says you add them all up, starting with the first rectangle and stopping at the nth. But now we're going to let the number of rectangles go to infinity. And by doing so, our error is 0. Our error is 0. So we just learned this is net area. That's what we called it. We called it net area by doing the summation notation with letting n go to infinity. That's the net area. But now we learn this net area is equivalent to this. And as we hit the next section, it's going to become, it should be mind-blowing if you understand the ramifications. But it's tied into this antiderivative thing, which is weird. I don't know, it is. So all I did, I wrote the expanded form. But this is just adding up a bunch of rectangles. So this integral antiderivative thing is adding up a bunch of rectangles. Now, this is going to have significance now because this f of x represents the height of a rectangle. This delta x represents the width of a rectangle, right? This dx is now the width of the rectangle. And this said you sum them up, right? This is an S for sum. And you start at A and you end at B. So the A is where you're starting your rectangles and B is where you're ending your rectangles. That's the starting and ending part. So in other words, this is net area. When you look at this, it's also net area. And it says start at A, end at B. This is your function or the height, and dx is your width. Now, I don't know if you remember, you should. Once upon a time, we did delta y over delta x, and we called that the average rate of change, right? And then we had something called dy dx, and that was called instantaneous rate of change. This was the slope of the secant line, and this is the slope of the tangent line. And the connection was rise over run, rise over run. But this was a rise and a run over a period of time to get that slope, right? But this was a rise and a run at a point because if you remember in the derivative, we let delta x approach 0. Delta x was the width or the distance between the 2 points, approach 0. So as delta x approaches 0, we said, hey, that's dx. But as the number of rectangles approaches infinity, your delta x, as the number of rectangles goes to infinity, your delta x approaches 0 again. So in this case, the delta x turned to dx. In this case, the delta x turns into dx. This means that the width is approaching 0. So, big takeaway. This notation here, this definite integral, gives you the net area. So if you want to figure out what this is, it is net area. Big, huge takeaway. A couple of notes, and this is bothersome for some people, but what's the difference between these three things? They have different variables, x, w, and s. But if I were to graph all these three, the only difference between the graphs, one would have an x for the x-axis, one would have a w, it's actually a Greek letter, but we'll call it w, and one would have a s for the x-axis. The graphs would look exactly the same. It's just a different name for the variable here on the x-axis. Now x or w or s. The graphs look exactly the same, just different variable. And so this says net area. This says net area. This is net area. What does the net area of all three of these, how do they compare? They're exactly the same. They're equal. So the significance of this is saying I can change my variable to anything I want to, and it's the same thing. The answer is the same. That comes into play, and you need to be okay with that. You need to be comfortable that I could change x to a w, and I haven't changed the answer. It's still the same net area. All right, for practice, try to do example 2. Try to find the definite integral from a to b of f of x dx. And after you've done that, come back and we'll compare answers. Welcome back. So this is net area. It is our summation. We're doing a sum of a bunch of rectangles. There's the height, there's the width, but the number of rectangles have gone to infinity, so it's the net area. So I have an area above, which is 1, so I'm going to be 1, minus the area below, but the area below is 2. And then this last one's above, so it's going to be plus 3. Now, actually looking at that, 1 represents the area above, 2 represents the area below, 3 represents the area above. So it should be 1 minus 2 plus 3. Now, I just realized this is not the actual areas, because that's not the scale. Because that's the smallest, that's the biggest, but that's 1, that's 3. But it's the area of 1 minus the area of 2 plus the area of 3. I'll just talk about it in those senses. I kind of messed up on that, but you get the idea. Let's just keep going, because you got the gist of this lesson, but there's going to be a few properties that we have to add. Okay, next example. How do I do this? I don't have a picture. I don't know what it looks like. But you do know what it looks like because you had Algebra 1. And you learned that's a line with a y-intercept of 3 and a slope of 2. Now, I'm not going to draw it to scale, but it's going to be like that. And I want the net area from 2 to 4. So from there to there. I can find that area. How? Well, at 2, if I plug in 2 here, that's 7. So I know the y value there is 7. And if I plug in 4 here, that's 11. So I know the y value here is 11. And I can draw some shapes. Look, there we go. So the height there is 7. This is 2. And this is 4. And so what is this integral, this definite integral? It's the area of our rectangle plus our triangle. The rectangle is 7 by 2, and the triangle is 1/2 the base times the height. So it's 14 plus 4, or 18. So this net area is 18. All right, you go ahead and try B, And I dare you to try C and see if you can do it. Go ahead and pause and then come back. Welcome back. Again, we have a line, y-intercept of -6, slope of 2, let's see. So we want the net area, wow, I drew this small, from 1 to 6. So you have two triangles, one below and one above. So we need to know the value right there to get the height of the bottom triangle. So if we plug in 1, because it's 1 to 6, we plug in 1, that's going to be -4. So we know that's -4. And we want to know the value there. So we plug in 6. 12 minus 6 is 10. So that's going to be 10. The width from there. Now I know it crosses, this equals 0 at 3. So that's going to be 3. So this is 3 to 6. So the width of that triangle is 3. And the width of this triangle is 2. And so the net area, we subtract the first one, 1/2. The base is 2, and the height is 4. And because that's negative, we're subtracting, because the y is negative. And then we add the area on top, which is 1/2. The base is 3, and the height is 10. So we're going to get -4 plus 15, and I get the answer of 11. Hopefully that's what you got. Unless I messed up, then hopefully that's not what you got. And I often make mistakes. But that's the answer to that one. This last one, you're going to look like, what the heck is that? I don't know how to do that. You actually do, you just don't recognize this. And so let me help you see what you don't see. I'm going to square both sides. And I'm going to move the x minus 3 to the left by adding it to both sides. Now, you should recognize that. It's the equation of a circle. That is a circle. X squared plus y squared equals 1 is a circle. This is r squared. This says the center is at 3, 0 with a radius of 1. So you do know what that looks like. It is a circle with a radius of 1. Oh, except the center's at 3, 0. Sorry. I messed up. Let me do this over again. The center's at 3, 0. And the radius is 1. So there's our center, and the radius is 1. It's going to be right there. There we go. All right. So, oh, and by the way, when we square root, it's only positive, so we'll only get the top half. It's only the top half of the circle. And so we want the integral from 3 to 4. We're adding up all of the rectangles, starting at 3 and ending at 4. So we're trying to find all those rectangles added up in that region. So the net area of that region. So just a reminder, when you see this, you should see, oh, I'm adding up. What am I adding up? Oh, this is the height of a rectangle, and this is the width. I'm adding up the area of a bunch of rectangles. And so this is going to be easy. The net area of this, the area of a circle is pi r squared. Pi r squared. Our r is 1, but this is not a whole circle. Of the circle, we only have 1/4, so we divide that by 4, so the answer is pi over 4. Hope you guys got that. We have done 3 definite integrals by using the area of familiar shapes. Let's keep going. Okay, can I fit all this on a page? Yes, I can. So here is your last example. Find these definite integrals. You will pause. I won't pause because that would be bad because then you'd be just sitting here watching nothing. But you'll pause and try these out, and I'll give you the answers, and we'll see how we do. All right? Welcome back. The first one, we're going from A to B. The area is 12, so that answer is going to be 12. The next one, we're going from A to C. So that area is positive. That area is going to be negative. Well, it's not a negative area. We're doing net area. So you subtract that area, which is 10. So it's going to be 12 minus 10, which is 2 for the net area. Let's keep going. And just a reminder, I'm going to remind you of these. Why is this negative when we find this integral, which is the sum of the rectangles? Because the height of this rectangle is negative because it's below. And the negative is going to give you a negative number. That's why these come out negative. All right, B to C. B to C only. Well, it's just below, so it's going to be negative 10. B to D. So I'm going to do negative 10 because that's below and positive 8. So negative 10 plus 8, which would be negative 2. And the last one, A all the way to D. So it's above 12 minus 10 plus 8. So it's going to be 12 minus 10 plus 8. And that's going to be 10. So pretty easy, I hope, net area. But this may be easy, but make sure you're making connections. Okay, let me go back and stress this importance. This integral, definite integral, is connected with Riemann sums. The function here represents the height of your rectangles. Remember what this represents. The height and width. F of x, that represents the height of that rectangle. Delta x represents the width of that rectangle. And you multiply them, and you get the area of the rectangle. So the connection, this is the height and width of a rectangle, and this is you add up all the rectangles from beginning to the end. Then we said we take the limit as n goes to infinity, and that made the rectangles get smaller and smaller where delta x approached 0, but we saw the error approach 0, and we call that the net area. And the final connection, this net area of adding up all the rectangles is this weird thing we learned, the antiderivative, but with starting and ending numbers. So this is your starting and ending. This is your height. That's your width. So that's just a reminder. That's important. You understand where all this comes from. So here are some things that you just have to know. So if you go start at A and you end at B, and A is, this doesn't have to be true. Not true. So if you start at A and end at B, you get a net area. But if you go backwards, you start at B and you go to A, you're going to get the opposite net area. The opposite. And we'll do some examples. It's going to be negative that. I'll go back to this. I'll do this. So if you integrate from A to B, that was 12. But if you integrate from B to A, you can get negative 12. Okay? So if you go backwards, it becomes opposite, it becomes negative 12. And the only explanation, people ask me why, this is actually a definition. They're telling you that when you go backwards, it comes out negative. But logically, to think of it this way, if you go backwards, now your delta x are negative. Your height's still positive, but your delta x becomes negative. So that's kind of how I think about it. But they're telling you, go backwards, opposite direction, your answer is opposite of what it was. And this next one is so much sense. If you start at A and end at A, it's 0. They're given that definition. To me, that's so obvious. What's the area under the curve starting at A, ending at A? It's going to be 0. You have no area because you haven't moved. So those are two that you have to know. This one is used all the time. This one, occasionally you'll see that, but not very often. Here is the next one. This should make sense. If I add the integral from A to C and then add C to B, so if I add this plus this, it's going to be the area from A to B. So A to C plus C to B is A to B. So that's your next property of integrals. So if you have an integral, and you're allowed to split that up, you can pick a point in between called C, and then take the integral from A to C, and then add C to B, and that's going to be the same as the original. So that just should make sense. That area plus that area is that area. So the integral from A to C plus C to B is A to B. Now, this one's similar but different. It's just rearranged basically. Okay? So if you take this whole thing and subtract that piece, it will give you that. That's what it's saying. So from A to B, that piece, you take this whole thing and you subtract that right piece. So we're just manipulating. If you go from A to B, you could take the whole thing A to C and subtract that right piece. And so you're just manipulating, and if you were to add this to the other side, it's just this. So it's just a different way of looking at it. Where it gets strange, remember I said you could pick a C here? Your C could actually be outside of A to B. It still works. Should I illustrate that? Maybe I will. I will. I should have just thought of this ahead of time. So suppose this is your A and this is your B. And we have an integral from A to B. And I said you can pick any C you want to. So let me shade this for you. Yeah, I'm just going to do a lazy shade. Yeah, that stuff right there. Yeah, ugly. It's kind of artistic, isn't it? Kind of pretty. Yeah, arty. Now, I said you can pick a C and split it up, and then A to C plus C to B, right? What's weird, I could pick a C out here. And it's still true that the integral from A to C plus C to B works. This is the same formula we have up here. A to C, C to B. The key thing is these have to be the same, and then it's the equivalent from A to B. A to B. So as long as these two numbers are the same. Well, we start at A. These two can... Whoa, that's messed up. I'm glad I did this. I just caught my mistake. That's C. That's the same as above here, but the C is outside. But as long as these are the same, then it's the integral from A to B. It doesn't matter if C is outside. And you may be like, whoa, that doesn't make sense. But let me show you. So if you do this A to C is all of this, right? You're going to say, that's too big. I only want the blue section. Well, what's this? C to B. I'm going backwards, right? When you go backwards, we learned we subtract that. So A to C is this whole thing here, but C to B is minus that. So I do end up with the blue part. That blew your mind? I'm sorry. Just understand the C does not have to be between A and B. to use the formula up here. A little mind-blowing, just throwing that out. So here's a summary of properties. And this is the end of the lesson, and then we're doing examples. So properties galore. This one where I said, if you start A, end at A, what's the area underneath that? Clearly 0. Start A, end at B. If you go backwards, B to A, it's going to be the opposite of that. Now, it doesn't matter if A is less than B, because if A is bigger than B, this will come out negative. And then when you go from B to A, the negative will make this positive, so it doesn't matter. Here's a new one. If you have two functions, you can split it up into two individual integrals of f and g. Here's the next one. If you have a constant integrating a constant, you can pull the constant out in front and it's the same. And this is the one we just show where you can split it up. Starting A, ending at B, any number C in between, and it's equivalent. So we have one example and we are done with this video. Here we go. They are telling us the integral from 0 to 5 is 3. And the integral from 0 to 7 is negative 10. We're going to try to see if we can figure out these 5 problems. Okay, we're going to use our properties that we learned. Hey, there's a constant. I learned I can pull that constant out in front. And then I just need to find that, but I have that. That's negative 10. So this is 2 times negative 10, which is negative 20. Dun, dun, dun. Oh, by the way, you should have paused and tried these. Welcome back. Magic of video and pausing. 5 to 7, how am I going to get that? I don't have a 5 to 7. But remember that property. And I'm going to not put all my f of x's and dx's because I don't have space here. I remember 0 to 7 is 0 to 5 plus 5 to 7. Remember that? That's that property. These have to be the same, then it's that to that. Well, what do I know? Do I know 0 to 7? Yeah, I do. That's negative 10. That's negative 10. Do I know 0 to 5? Yeah, I do. That's 3. And then I have 5 to 7. So the integral from 5 to 7, this is going to be that minus that, because I have to subtract that. So it's going to be negative 13. Tricky. That is a really common question on multiple choice AP tests. So if that seems hard to you, process through what just happened. Okay? That is very common. This one's easy. 5 to 0. 0 to 5 is 3. 5 to 0 is the opposite. Constant, I pull the constant out. What is this? 7 to 0. Well, 0 to 7 is negative 10. So 7 to 0 is going to be opposite. It's going to be positive 10. So that's 60. And our last one and the end of this video. A lot of you would see this and say absolute value. Let me erase the thing above. It's crowding me. Back off, back off. Absolute value. Oh, that's easy. That was negative 10. The answer, positive 10, right? Woo-hoo-hoo. Maybe. But let me show you why we do not know. Here is 5. Here is 7. So it looks like the area above is 3, right? From 0 to 5. So you might assume it's going to have an area of 3 here. And then 0 to 7 is negative 10. So that means if this is 3, this must be negative 13, right? Negative 13? We said 5 to 7 is negative 13. So that must drop way down here. And this area must be 13. And then you say, okay, 0 to 7 was 10. So 3 minus 13, that's negative 10. So 0 to 7 absolute value, okay, you wouldn't say it's positive 10. Wow, I just messed up. Some might say this. That's wrong anyways. You don't have to. Some say, oh, but absolute value, what does it do? It's going to pop this part up top. And it's not going to be below anymore. So the answer is 16, right? Yeah, 16. That would be wrong. You don't know it's 16. And here's why you don't know it's 16. And you may think it has to be. This was 3. Negative 13, the area here is 13. Now I move at the top, 3 and 13, 16. Again, you don't know that, and I'll show you why. You're making assumptions that you don't know. Could it not look like this? Could it not go way down and then back up like this? We know from 5 to 7 is negative 13. Could this not have an area of 1 there and 14 there? And would it then 5 to 7 would still be negative 13, but it could have a portion below and a portion above. Then when you absolute value, all of this will move up top, giving you a 14. And now your net area will be 3 plus 14 plus 1, 14, 17. Now it's 18. So you don't know what this looks like. And this could be even more dramatic than what I just drew. Could it not go way down here and way up here? And this be 3 and this be 16? So our net area here is still negative 13. You don't know what it looks like. Then when you absolute value, this would go up top. You'd have 16. And now you're going to have 16 and 6. You're going to have 22. So this cannot be figured out. That is the end of this video. Hopefully it wasn't too bad. Bye-bye.